Welcome back to the deep dive. You know, those deep dives we do into philosophical topics. Today we're going to be tackling something that has kept philosophers up at night for centuries and has made us toss and turn, I'll tell you that much, paradoxes.
Ah, yes, paradoxes.
Paradoxes are more than just quirky logical puzzles. For us, they're invaluable tools for probing the very edges of thought, pushing against the limits of what we can say and understand in a way that remains consistent. Think back to Zeno's paradoxes, that feeling that motion shouldn't be possible if you break it down infinitely. Or the early stabs at truth and falsehood that the Mengerian school grappled with. These weren't just abstract games, they were fundamental inquiries into the nature of reality and the structure of our reasoning.
Absolutely. And it's so fascinating to trace how these ancient stumbling blocks, these head scratchers that really made people question things, they've become cornerstones of modern logic.
Yeah, how did that happen?
Well, what began as a way to kind of dismantle arguments has, through rigorous investigation, blossomed into profound insights that continue to shape how we think about deduction and truth.
So, like a tool for breaking down has become a tool for building up.
Exactly. A tool for analyzing the very foundation of thought.
So in this deep dive, we're going to be looking specifically at the period between the dawn of the 20th century and 1945, a real hotbed for dissecting logical paradoxes and forging concepts that are still central to logic today.
A pivotal period, for sure.
And just to be clear for you, we'll be using paradox and antinomy in a pretty interchangeable way.
Okay, fair enough.
And while many of the things we'll be looking at do involve outright contradictions, statements that are both true and false, not all of them do, our aim today is to really extract those core logical themes, the ideas that emerged from those early 20th century philosophical and logical debates. We're not going to delve into paradoxes involving vagueness or knowledge or belief, or even space and time today. Those are rabbit holes, perhaps, for another deep dive.
Definitely enough material there for another day.
Our focus today is laser sharp on those logical foundations.
It's like we're zeroing in on the core.
Exactly.
And it's vital to appreciate the sheer impact these early paradoxes had. They weren't just abstract brain teasers for logicians to play with.
Yeah, they really shook things up, didn't they?
Oh, absolutely. They shook the very ground on which we built our understanding of sets and collections, those fundamental building blocks of much of modern mathematics and logic. And they forced a complete reevaluation of the basic rules of syntax and even the meaning of our terms, how we define things within standard classical logic.
Okay, so these paradoxes created a bit of a crisis in the foundations of logic.
You could say that.
What were some of the key ideas or theories that emerged as philosophers and logicians wrestled with them?
Well, I think it's safe to say that this drive to resolve these deep inconsistencies spurred some really foundational work. It directly led to the first rigorous axiomatizations of set theory, attempts to provide a solid and consistent foundation for dealing with collections. We also saw the systematic development of type theory.
Type theory.
Yeah.
Can you remind us what that is again?
Sure. Type theory is kind of like a hierarchical way of organizing our concepts to avoid this problematic self-reference that we see in the paradoxes. It's a way to keep things sorted and prevent those contradictions from popping up.
It's like putting things in their proper boxes.
Exactly. And perhaps most fundamentally, it spurred the very foundations of formal semantics, which is really the study of meaning in a very precise and structured way. How do we assign meaning to our logical and mathematical symbols?
And isn't this where the distinction between predicative and impredicative definitions comes in?
You got it. It was a major philosophical byproduct of all this turmoil. This crucial conceptual split between predicative and impredicative definitions has really had a lasting impact on how we understand mathematical existence. And, what are the limits of constructivism? What can we actually build up logically?
Okay, so when did this intense period of paradox exploration really kick off? What were the main philosophical battlegrounds between, say, 1897 and 1917?
Right, so we're zeroing in on a specific time frame now.
Yeah, let's narrow it down a bit.
We saw significant philosophical grappling in a few key areas. First, you had the puzzles surrounding ordinal and cardinal numbers. Think Borelli-Forti and Cantor.
Okay, those are big names in the world of infinity.
They are. Then you have the paradoxes concerning properties, sets, and classes, Russell's contradiction being the most famous, but also Zermelo was right there with him. A third crucial area involved propositions and truth, again, with Russell playing a pivotal role in exposing the philosophical difficulties.
It's amazing how much one person can contribute.
He was a prolific thinker. And finally, we have the paradoxes arising from the very notion of definability. What does it mean to define something precisely?
Right.
And how this notion of definability tangled with the continuum, the heart of real analysis. There are important contributions from thinkers like Richard, Koenig, Bernstein, Berry, and Grelling. Now, some of these paradoxes, like the liar and Russell's, those have, as you pointed out, vast philosophical literature. We can spend hours on each one. But here, we're interested in the connections between them.
Yeah, the bigger picture, how they all fit together.
And how they, shifted the landscape of foundational and philosophical debates about the nature of logic and mathematical objects.
Okay, so let's zoom in on those early numerical paradoxes.
All right, sounds good.
What was it about ordinal and cardinal numbers that was causing such philosophical headaches?
Well, it began, in 1897 with Burali-Forti. He was actually trying to demonstrate that the ordinal numbers couldn't be linearly ordered.
They couldn't be linearly ordered. That seems counterintuitive.
It does, doesn't it? And while his proof had issues, what emerged was a profound problem with the very idea of a collection of all ordinals.
Uh-oh. That sounds ominous.
It was a big deal. He essentially showed that if you assumed such a collection formed a well-ordered set, and remember, the ordinals themselves are defined to be well-ordered, you'd immediately arrive at a contradiction with a very well-established theorem about well-ordered sets and their ordinal types. So the philosophical upshot was clear. This intuitive notion of a totality of all ordinals just didn't hold up logically.
It was like trying to fit an infinitely large object into a finite box.
A very apt analogy.
So Cantor, the architect of set theory himself, was also grappling with similar conceptual boundaries around the same time, right?
He was. As early as 1895, Cantor had observed similar difficulties, particularly when contemplating the set of all conceivable sets. If we were to assume this formed a legitimate set, call it M, it would possess a cardinal number, which would, by definition, have to be the largest possible cardinal number.
It would be like the king of all cardinal numbers.
Right. But then Cantor's own theorem, his groundbreaking theorem, established that the power set of M, the set of all its possible subsets, would always have a cardinality strictly greater than. So there's their contradiction, the very idea of a set of all sets. It's like a snake eating its own tail.
It just implodes on itself. So how did they try to make sense of this?
Well, Cantor introduced a distinction that at first people were a bit skeptical about. He distinguished between inconsistent totalities, those that can't be conceived as a coherent whole, like the set of all sets and completed totalities, those that can be regarded as finished and well-defined entities.
Okay, so the inconsistent ones are too big, too unwieldy.
Too vast. And the completed ones are more manageable. And this distinction, this attempt to reconcile our intuitive grasp of collections with the logical demands revealed by the paradoxes, it foreshadowed later debates about the nature of classes versus sets. It's like a philosophical seed that was planted.
So how did this distinction help in understanding Burali-Forti's paradox specifically?
In the context of Burali-Forti's paradox, Cantor's distinction implied that the multiplicity of ordinal numbers, while well-ordered, didn't qualify as a set in the strict sense.
It was one of those inconsistent totalities.
It was. It wasn't a completed totality. Therefore, you couldn't consistently assign an ordinal number to it, and the paradox dissolved.
It's like saying, this thing is so big it doesn't even fit into our system of ordinal numbers.
Precisely. And I think this highlighted a growing philosophical awareness that we needed to carefully delineate the boundaries of these fundamental concepts. What is a set? What is a collection? What are the limits of these ideas?
Okay, so that really sets the stage for Russell's arrival and his infamous contradiction. What made his paradox so groundbreaking?
Well, Russell's contradiction, which he formulated around 1901, was a bombshell.
It really was. It sent shockwaves through the mathematical world.
It did. And it was so striking because of its simplicity and its direct assault on the very foundations of logic. Unlike the complexities of transfinite arithmetic, Russell's paradox hinged on this basic idea of predicate application. It had this remarkably clear element of self-reference.
Right, this idea of a property referring to itself or a set containing itself.
Exactly. He asked us to consider the property of being a property that cannot be predicated of itself. If this property can be predicated of itself, then by its own definition it cannot. Conversely, if it cannot be predicated of itself, then it perfectly fits the definition and therefore can.
It's a mind-boggling loop. You can't escape the
A
contradiction.
logical trap.
So what was the fallout from this?
Well, Russell extended this to classes. There's no class of those classes, which, taken as a totality, do not belong to themselves. The conclusion was unsettling. Under seemingly innocuous conditions, a perfectly definable collection just doesn't form a coherent totality.
Yeah.
This had a devastating impact on this philosophical program of grounding all of mathematics in pure logic, where set membership just mirrored predicate application without any restrictions. This was the view championed by Frege.
It's like the rug was pulled out from under Frege's entire project.
You could say that.
So how did Russell respond to this crisis?
Well, in his Principles of Mathematics from 1903, he meticulously explored this paradox, looking at it from all these different angles. He even adapted it to argue that a propositional function couldn't be treated as a logical subject in itself. Something like x is mortal, where x is the argument.
Right. The propositional function needs something to be about.
It does. It can't just stand alone. And trying to treat it as a subject led to the same kind of inconsistency. It suggested this deep philosophical connection between how we understand properties, classes, and the very structure of predication, how we say things about things.
It's like the paradox was revealing these hidden connections between different areas of logic.
Exactly. It was forcing us to rethink how these fundamental concepts related to each other.
He also drew a connection to Cantor's theorem, didn't he? About our limitations in enumerating properties.
He did. Russell formulated a version of Cantor's theorem that beautifully captured the mechanism of diagonalization.
Diagonalization, that's a powerful technique.
It is. The technique Cantor used to prove the uncountability of the real numbers. Russell showed that no binary relation could fully parameterize all unary predicates over a given domain.
Meaning you can always find a property that escapes your attempt to list them all.
You got it. It's like the properties are always one step ahead of us. Philosophically, this suggested an inherent open-endedness to the realm of properties. No matter how comprehensive our system is, we can always construct a new property that falls outside it.
It's like there's always more to discover, more to define.
Exactly. And that has really deep implications for our understanding of the limits of formalization and the power of language.
So the big question is, what was the core dilemma that Russell's contradictions laid bare? What fundamental principles were at odds with each other?
It was this tension between two very basic logical principles. The comprehension principle and the idea that every class can be treated as a unified entity.
So on the one hand, you have this idea that every well-defined property should have a corresponding class, like the set of all things that have that property.
Right, like the set of all red things or the set of all even numbers.
And on the other hand, you have the idea that every class should be treatable as a single thing, a term in logical discourse.
It's like saying, okay, we can group these things together and then talk about that group as a whole.
But Russell's paradox showed you can't have both.
It showed that holding on to both of these principles leads to contradiction. It's like a fork in the road, Philosophically, we were forced to choose which principle we had to abandon or restrict, which had huge implications for how we thought about the relationship between properties, classes, and the very structure of logical thought.
So Russell proposed the doctrine of types as a solution to this.
He did. It was a radical proposal, a completely new way of thinking of the foundations of logic.
Remind us again, how did the doctrine of types work?
Okay, so the central idea is that every propositional function has a specific range of significance, or a type, and it can only be meaningfully applied to objects that belong to that type.
It's like saying you can't mix apples and oranges.
Right. Or
Yeah.
you can't apply the property red to numbers.
So these types form a hierarchy.
They do. At the base, you have individuals, the most fundamental entities. And you have classes of individuals, and then classes of individuals, and so on. So it's like a multi-level structure.
And the core principle is that a function must be of a higher type than its arguments.
That's the key. This prevents that kind of self-application that fueled the paradoxes.
It's like a safeguard, preventing the system from collapsing in on itself.
Precisely.
But even with this initial idea of types, there were still challenges, right? Especially when it came to propositions.
Right, because if you treat all propositions as belonging to a single type, you run into problems.
Problems like,
Well, for one, you could argue that there are at least as many propositions as there are objects in your domain. And then if you could form types of propositions, Cantor's arguments would suggest there are more types of propositions than propositions themselves, which is kind of weird.
It's like saying there are more categories than there are things to categorize.
Exactly. A very counterintuitive result. And Russell also explored this idea of a logical product of propositions, like an infinite conjunction. And he found that if you weren't careful about the types of propositions involved, you could end up with contradictions again.
So it wasn't as simple as just introducing types. You needed to be very specific about how they worked.
It was more nuanced than that. It hinted at the need to further structure propositions into different types, which had big implications for how we thought about logical complexity and truth.
And this led to the development of the ramified theory of types, a more elaborate system.
Exactly. But it's important to remember that initially, Russell was actually quite hesitant to embrace the full complexity of the ramified theory.
He was reluctant. Why?
I think, from a philosophical standpoint, he found the idea of needing multiple types for propositions to be inelegant, a little artificial. He even speculated that the collection of all propositions might be a counterexample to Cantor's theorem, which shows how much his thinking was evolving.
It's fascinating to see how even the greatest minds can struggle with these ideas.
It shows the depth of the problem.
So while Russell was grappling with these fundamental logical principles, other mathematicians like Hilbert and Zermelo were also confronting the paradoxes, right? But from different angles.
Oh, they definitely were. And their responses were quite illuminating.
Can you tell us about Zermelo's approach?
Well, Zermelo, working in Göttingen, realized that a set that contained all its subsets as elements would lead to a contradiction. He essentially recreated Russell's paradox in the context of sets, focusing on the subset of M containing all elements of M that weren't members of themselves. This reinforced the growing sense that the intuitive idea of a set needed some serious revision.
It's like they kept hitting this same wall, this fundamental limitation of self-reference.
It was a persistent problem.
So what about Hilbert? How did he approach this?
Well, Hilbert was exploring contradictions arising from what he called closure conditions on a set. If you had a set that contained the natural numbers and was closed under certain operations like taking power sets or forming unions, you could derive a contradiction.
It's like saying if you make the set too powerful, it becomes unstable.
Exactly. And he also developed a fascinating functional version of Russell's paradox, based on the idea of a universal domain containing everything and allowing for functional self-application. This functional interpretation was really influential, and it later played a role in the development of things like combinatorial logic and lambda calculus.
So they were exploring the limits of self-reference in different formal systems.
They were. And despite all these challenges, the Hilbert school remained optimistic. They didn't see these paradoxes as a reason to give up on the search for truth.
They had a very different philosophical attitude.
They did. For Hilbert, contradictions were signs that our logical tools were too crude. They were an impetus to develop more refined methods, a deeper understanding of how we form concepts.
So the paradoxes were seen as challenges, as opportunities for growth.
Exactly. As signposts pointing towards a more rigorous metamathematical analysis of proof and the axiomatic method.
They believed that by refining our formal systems, we could overcome these obstacles.
Exactly. And that the consistency of the axioms would ultimately guarantee the legitimacy of the concepts we were working with.
So around 1905, the focus seemed to broaden beyond these foundational questions of sets and logic, with new paradoxes emerging that dealt with the concept of definability.
It was a very fertile period,
Yeah, what sparked this shift in focus?
Well, there were paradoxes emerging that engaged with the structure of the continuum, those age-old questions about whether it could be well-ordered and the status of Cantor's continual hypothesis, and the concept of definability took center stage.
Definability. What exactly does that mean in this context?
Well, it's the question of what it truly means for a real number, or any mathematical object, to be definable in a finite, precise way. Can you specify it unambiguously using language? That became a key point of contention.
I see. So it's about the relationship between language and mathematical objects.
Exactly. And one of the most striking examples is Koenig's attempt to refute Cantor's continuum hypothesis.
Ah, yes, that famous hypothesis about the size of the continuum. What was Koenig's argument?
Well, in 1905, he presented an argument based on this idea of real numbers being definable in a finite number of words. He said, look, the collection of all definable reals has to be countable, right?
Because there are only countably many finite strings of words.
Precisely. But the continuum is uncountable, so there must be real numbers that are inherently undefinable. Then, assuming that the continuum could be well-ordered, he considered this least real E, which is not in the sequence of definable reals.
Okay, I see where this is going.
The paradox is that this very description, the least real E, which is not the sequence of definable reals, seems to define E in a finite number of words, meaning it should be in the sequence. And that's the contradiction.
It's like the definition itself pulls the rug out from under the argument.
Exactly. And Koenig's proposed solution involved invoking Cantor's distinction between inconsistent and completed totalities, arguing that Cantor's second number class, the collection of all countable ordinals, wasn't a set in the proper sense because you couldn't definitively distinguish its elements from one another.
So the collection is too big, too vague to be a proper set.
Right. And this connected to a broader debate about the criteria for legitimate mathematical existence. Can something exist if you can't even define it precisely?
Now, Richard's paradox also grappled with definability, but it didn't rely on the well-ordering of the continuum, right?
You're absolutely right. Richard's paradox took a slightly different approach. He imagined an enumeration of all real numbers that could be defined by a finite number of French words.
Why French?
I think it was just an arbitrary choice, just to specify a particular language.
Okay, makes sense.
Then he came up with a procedure for defining a new real number, n, based on the decimal digits of the numbers in this enumeration, ensuring that n would be different from every number on the list. So far, so good.
Right. Seems like a clever way to construct a new number.
It is. But the problem is, this new number n seems to be defined by a finite number of words itself, right?
I see the problem. If it's definable, it should have been in the initial list.
Exactly. And that's the paradox.
Yeah.
So Richard's proposed resolution centered on this idea of vicious circularity in definitions, a concept that became quite influential.
Vicious circularity. Tell us more about that.
Well, Richard pointed out that the definition of his number n referred to the totality of all definable reals, which, if n were definable, would have to include n itself.
So it's like the definition is biting its own tail.
Precisely. He argued that you shouldn't be able to define something in terms of a collection that already presupposes its existence. That's the vicious circle. And this idea became a cornerstone of Poincaré's critique of impredicative definitions. Those that define something in terms of a totality that includes the thing being defined.
So it's about the order in which you define things. You can't define something in terms of something that depends on it already existing.
It's a subtle but crucial point. And it shows a growing awareness of the dangers of self-referential definitions.
So these debates about definability were also tied to the nature of the continuum itself, right?
Oh, absolutely. Thinkers like Bernstein were deeply engaged in this. He even claimed to have resolved Cantor's continuum hypothesis.
Oh, really? How so?
Well, his argument was based on the idea that the continuum could be built up from computable real numbers. Those that have an explicit algorithm for generating their decimal expansion.
So a more constructive approach to the continuum.
Exactly. He controversially claimed that there were uncountably many such computable reals arranged in a hierarchy. Now, his mathematical claims didn't quite hold up in the end.
They didn't, no.
But his philosophical intuition about the importance of definability and constructibility was remarkably prescient. It foreshadowed later developments in set theory, especially Gödel's work on the constructible universe.
So even when the specific mathematical details were wrong, the philosophical ideas were still valuable.
Absolutely. It's often the case in the history of ideas.
So there was also this underlying debate about what could count as a legitimate rule for defining an infinite set.
Oh, yes. This was a huge philosophical divide.
What were the main camps in this debate?
Well, on one side, you had thinkers like Borel, Baire, and Lebesgue, who insisted that mathematical entities only truly existed if they could be named by a finite number of words.
So a very strict finitistic viewpoint.
Very much so. They were suspicious of anything that couldn't be explicitly defined. On the other side, you had mathematicians like Hadamard and Zermelo, who had a more Platonistic perspective. They believed in the objective existence of mathematical objects, regardless of whether we could define them or not.
So a more abstract, perhaps even metaphysical view of mathematics.
Precisely. And this debate was intertwined with all sorts of foundational questions, like the well-ordering problem and the classification of discontinuous functions.
So it wasn't just about sets, it was about the very nature of mathematical existence and how we come to know mathematical truths.
Exactly. It was a debate about the limits of our knowledge and the power of our methods.
So moving into the period between 1905 and 1913, we see the emergence of predicativism as a philosophical program and the continued development of the doctrine of types. It seems like the paradoxes really spurred a lot of creative thinking in the foundations of mathematics and logic.
They absolutely did. This was a period of intense debate and philosophical ferment, marked by new paradoxes like Berry's and Grelling-Nelson's renewed scrutiny of the liar paradox, and Russell's attempt to synthesize all these ideas into a comprehensive framework.
So let's dive into this clash between Poincaré and Russell on the nature of the contradictions. What were Poincaré's main objections to the logicist and axiomatic approaches to foundations?
Well, Poincaré was a staunch critic of both logicism, the idea of reducing all mathematics to logic, and the axiomatic method, which was gaining traction at the time. He was more aligned with an intuitionistic Kantian perspective.
What does that mean exactly?
Well, he believed that certain fundamental mathematical principles, like the principle of induction or the axiom of choice, were not derivable from logic alone.
They were not just logical truths.
They were more than that.
Yeah.
He argued that they were synthetic a priori judgments, truths grasped through kind of mathematical intuition.
So there's an element of human insight, of a kind of direct understanding that's not reducible to pure logic.
That was his view.
And he specifically criticized Russell's definition of natural numbers, right?
He did. Poincaré took issue with Russell's definition of natural numbers as those belonging to all recurrent classes, classes that contain zero and are closed under the successor operation.
It seems like a pretty straightforward definition. What was his problem with it?
His objection was that this definition was impredicative. It referred to the totality of all recurrent classes, a totality that would include the very class of natural numbers being defined.
So it's circular in a sense.
Exactly. For Poincaré, this was a vicious circle, and it rendered the definition inadmissible. He believed that mathematical objects should be defined predicatively,
Meaning
their definitions shouldn't rely on totalities that already presuppose their existence.
so you can't define something in terms of something that depends on it already being there?
Precisely. That was his fundamental principle. And it stems from his philosophical commitment to constructive methods in mathematics. He was wary of definitions that seemed to create things out of thin air. He wanted a more grounded, step-by-step approach.
And Poincaré's understanding of predicativity itself evolved over time, didn't it?
It did. While he always emphasized the need to avoid vicious circles, he later characterized predicative definitions in terms of their invariance. The idea is that a predicative classification should remain stable even if you introduce new objects into your domain.
So it shouldn't be affected by additions to your universe of discourse.
Exactly. It should be, in a sense, absolute. This later perspective foreshadowed modern notions of absoluteness and invariance that are central to contemporary set theory.
And he also reformulated Richard's paradox through this lens of predicativity, right?
He did. He essentially argued that there is no definable enumeration of definable reals. This formulation really captured his concern about the limits of definability and his commitment to the predicative ideal.
It's amazing how these paradoxes kept pushing these thinkers to refine their concepts and their philosophical positions.
It was a constant process of refinement.
So while Poincaré focused on predicativity, Russell took a slightly different approach.
He did. Russell was more concerned with the comprehension principle itself. He saw that as the root of the problem.
Remind us again, what was the comprehension principle?
It's the idea that every well-formed property defines a corresponding class. Like, if you can define a property, you should be able to collect all the things that have that property into a set.
Okay, and that's where the paradoxes arise.
Exactly. The paradoxes show that this principle, when applied naively, led to contradictions. So Russell's challenge was to figure out which propositional functions could define classes without generating these inconsistencies.
So it was a matter of finding the right restrictions on the comprehension principle.
Precisely.
And he was also influenced by Poincaré's emphasis on avoiding vicious circularity, wasn't he?
He was. He fully embraced the vicious circle principle, which says, essentially, that you can't define something in terms of a totality that includes the thing being defined.
So again, no self-reference, no circularity.
It was a guiding principle for him.
But this principle itself wasn't a complete theory, right? It was more like a constraint on what a good theory should look like.
It was. And Russell explored various approaches to actually implement it. He had this idea of zigzag theories, theories of limitation of size, and even the radical no-classes theory.
Can you tell us a little more about those?
Sure. The zigzag theory was an attempt to identify those simple or predicative propositional functions that could define classes without trouble.
Okay, so like finding the good ones that don't cause problems.
Right. The theory of limitation of size suggested that maybe legitimate classes had to be restricted in their size or complexity to avoid those paradoxical totalities. And then the no classes theory was really radical. It suggested that maybe classes weren't fundamental entities at all.
That's a bold move.
It was. It proposed that maybe they're just convenient abbreviations for talking about their members.
So like a shorthand way of speaking about collections.
Exactly.
So Poincaré and Russell also disagreed about the role of infinity in generating these paradoxes.
They did. Poincaré believed that the actual infinite was the culprit. That it was these vast, completed totalities that led to the trouble. But Russell disagreed.
He did. How so?
Well, he pointed out that paradoxes like the liar paradox don't involve infinity at all. They arise from self-reference and the nature of truth, not from dealing with infinite collections.
So the problem was deeper than just the infinite. It had to do with the very structure of language and how we talk about truth and falsehood.
Precisely.
And how did Russell analyze the liar paradox within this framework?
He argued that the liar sentence, that this statement is false, implicitly involved a quantification over all propositions.
It's saying something about every possible proposition.
Right. And therefore, according to the vicious circle principle, it couldn't itself be a proposition within that totality.
So it's not a genuine proposition, it's a kind of semantic anomaly.
Exactly.
Yeah.
And it's false precisely because it violates the rules of the game. It's like trying to use a word in a game where that word isn't allowed.
It breaks the system.
Precisely.
And he also looked at Berry's paradox, which is interesting because it involves finite numbers.
Right. Berry's paradox, the least number not definable with less than 18 syllables, seems to create a contradiction within the realm of finite things.
How so?
Well, the very act of defining the least number not definable with less than 18 syllables seems to use fewer than 18 syllables, which is the paradox.
It's self-contradictory.
It is. And Russell would likely have argued that this definition